Good day to everyone. I am Ryan Christian Marasigan from Electronics Communication Engineering, third year, section 1, and I'm here to discuss to you the dipole. So, the dipole fields which we shall develop in this section are quite important because they form the basis for the behavior of the electric materials in electric fields. And as discussed in part of the following chapter, as well as justifying the use of images as described in section 5.5 of the next chapter. Moreover, this development will serve to illustrate the importance of the potential concept presented in this chapter. So, before we actually start, let us first define dipole. An electric dipole, or simply a dipole, is the name given to two-point charges. This will be point Q and another point Q, wherein they are equal in magnitude and have opposite signs separated by a distance d. This will be their distance, which is small compared to the distance to the point P at which we want to know the electric and potential fields. So this will be the point P. And the distant point P is described by the spherical coordinates r. Here is r, this is r, theta, and P, which is 90 degrees, in view of the azimuthal symmetry. The positive and negative point charges have separation d and Cartesian coordinates 0, 0, 1 half d. This will be 0, 0, 1 half d and 0, 0, negative 1 half d. So much for the geometry. What would we do next? Should we find the total electric field intensity by adding the known fields of each point charges? Would it be easier to find the total potential field first? In either case, having found one, we shall find the other from it before calling the problem solved. And if we choose to find E first, we shall have two components to keep track of in spherical coordinates. And then the only way to find V from E is by the use of the line integral. This last step includes establishing a suitable zero reference for potential, since the line integral gives us only the potential difference between the 2 points at the ends of the integral path. So this will be the formula for B. This will be from the first charge to the second charge, which is also equivalent to so now note that the plane Z is equal to 0 midway between the 2 point charges. This will be midway, is the locus of points for where R1 and R2 is equal and is therefore at 0 potential and are all points at infinity. So for a distant point, R1 is equal to R2 and the R1 R2 product in the denominator may be replaced by R squared. So this can be replaced by R squared. The approximation may not be made in the numerator, however, without obtaining the trivial answer that the potential field approaches 0 as we go very far away from the dipole. Coming back a little closer to the dipole, we see R2 and R1 may be approximated very easily if R1 and R2 are assumed to be parallel. So they are assumed to be parallel. This will be R2 and this will be R1. Then this will be R1 minus R2, which clearly shows that it is equivalent to cosine theta. And again, the final result will be equal to this. And again, we should note that the plane z equals 0 and theta is equal to 90 degrees is at 0 potential. And by using the gradient relationship in spherical coordinates, we can get the value of E. Which is equal to negative gradient V. Then substituting, this will be the result. Then we will obtain the value of E. So for the correction, this is not squared, this is cube, r cube. Then E would be over 4 pi permittivity r cube multiplied by 2 cosine theta a sub r plus sine theta a sub theta. This will be the value of our E. So now we will be talking about the potential field. The potential field of the dipole may be amplified by making use of the dipole moment. Let us first identify the vector length directed from negative q to positive q as d, and then define the dipole moment as ud and design it at the symbol p. Thus, p is equal to qd. The units of p is c dot meter, since q is for charge and d is for the distance, which is in the units of length. Then since d dot product with ar is equal to d cosine theta, we then have b is equal to p dot ar over 4 pi permittivity r squared. This result may be generalized as b is equal to 1 over 4 pi permittivity multiplied by r minus r prime squared p dot product with r minus r prime over magnitude of r minus r prime, where r locates the field point P and r prime determines the dipole center. R is the field point and r prime is the dipole center. And always remember that this equation is dependent on any coordinate system. The dipole moment P will appear again when discussed in the electric material, since it is equal to the product of the charge and the separations, neither the dipole moment nor the potential will change as Q increases and D decreases, provided the product remains constant. The limiting case of a point dipole is achieved when we let D approach zero and Q approach infinity such that the product P is finite. Now, turning our attention to the resultant fields, it is interesting to note that the potential field is now proportional to the inverse square of the distance, and the electric field intensity is proportional to the inverse cube of the distance from the dipole. Each field falls off faster than the corresponding field for the point charge, but this is no more than we should expect because the opposite charges appear to be closer and greater distances and to act more like a single point charge of zero coulomb. So that will be the end of our discussion. Hope that you learn something on our lesson. Goodbye and thank you.